Hi, everyone. Thanks for braving an extreme environment outside to come here and listen to me talk about another one out in outer space. Um, so as many of you know, and as Ben just mentioned, 2019 is a big year for space history. It is the 50th anniversary of the Apollo 11 lunar landing that happens on July 20th. And as part of the commemorations, as Ben mentioned, the Linda Hall Library has an exhibit opening on March 28th called To the Moon, The Science of Apollo, which includes that special lecture Ben mentioned, including author Andrew Chaikin and Apollo 17 lunar module pilot Harrison Jack Schmitt, one of the two final astronauts to set foot on the moon in 1972. So a real special opportunity there, and I hope all of you can make it out to that. Since my research focuses on the space sciences before NASA and before the space race, my talk today can serve as sort of a prelude to the Apollo lecture and exhibit next month. In the first part of my talk today, I'll tell you about my PhD dissertation, Anticipating the Astronaut, which is about the early history of space medicine, the science of selecting and protecting astronauts in space. Then I'll switch gears and tell you a little bit about my current project, the one I'm working on here at the Linda Hall Library, which is about the origin of astrobiology, the potential study of extraterrestrial life, especially with regards to the planet Mars. In both cases, I'll focus on the period between World War II and the creation of NASA in 1958, when these sciences were exclusively a military concern. In space history, the story of NASA and the triumph of Apollo tends to overshadow this earlier military period, when space science was more obscure, less well-funded, and not exactly a national priority. But it was in this military moment that many aspects of spaceflight and of space science made their debut. And these nearly forgotten stories can help us see spaceflight in new and different ways. So first, space medicine and the astronaut. Usually the history of astronauts starts in 1959 with NASA's selection of 7 military test pilots for Project Mercury, a group called the Mercury 7. But early in my research into the origin of the astronaut, I decided that this group would serve as the end of my story rather than the beginning. Instead of the familiar NASA astronauts like John Glenn and Gordon Cooper and Neil Armstrong, my dissertation looks at 4 nearly forgotten astronaut experiments in military space science, in space medicine in particular. And these experiments featured test subjects that are strikingly different than the iconic male military test pilot that NASA made famous in the 1960s. My goal in recovering these obscure experiments is to show how different versions of the astronaut were in the mix early on, and to get people to think differently about who we send to space and why. So the central figure in the history of American space medicine is this man, Hubertus Strughold. He's a German doctor, medical doctor, who also had a PhD in physiology. He was sort of a lesser-known Wernher von Braun, but of the life sciences instead of rocket science. Both von Braun and Strughold came to America after World War II as part of Operation Paperclip, along with roughly 1,500 other German scientists. Most of these were engineers and physical scientists. There was about 40 life scientists included in this group, so doctors, physiologists, psychologists, that sort of thing. Strughold stood out amongst the paperclip population as the leading expert in a field called aviation medicine, the field responsible for selecting and protecting military pilots. While von Braun ended up in Huntsville, Alabama, designing rockets for the Army and eventually NASA, Strughold went to the United States Air Force's School of Aviation Medicine in San Antonio, Texas. From his post at SAM, Strughold worked on new problems America faced in the Cold War, like keeping bomber pilots alive high in the upper atmosphere, which, from a medical standpoint, presented similar problems to spaceflight. Above 50,000 feet, the air is so thin and so cold that humans lose consciousness and asphyxiate in nearly the same way as they would in space, and require similar protection, a totally sealed, pressurized environment. After Strughold convened a small symposium on the medical problems of spaceflight in 1948, the Air Force decided to create a new department at the School of Aviation Medicine, the Department of Space Medicine. It was the first of its kind anywhere in the world, and Strughold was the obvious choice to lead it. With a staff of 3 other German scientists, all participating in Operation Paperclip, Heinz and Fritz Haber and Konrad Buttner, Strughold set out to solve the medical problems of spaceflight, which included the intense forces of acceleration and deceleration, thin, low-pressure atmospheres, radiation exposure, temperature extremes, the strange state of zero-G, or weightlessness, but also the psychological problems of isolation, confinement, and monotony. The motto Strughold chose for his new department of space medicine was Astronautico Subvenimus, which is Latin for "we support the astronaut." But because astronauts didn't exist yet, they did much more than just support the astronaut. They created the astronaut. When NASA was finally founded in 1958, the agency lacked medical expertise, so they drew heavily on this Air Force space medicine. Strughold's work was so influential that he became known as the father of space medicine. So now that I've introduced you to Strughold and his Department of Space Medicine, I can take you through the 4 astronaut experiments that I explore in my dissertation, Anticipating the Astronaut. The first is this device called the Space Cabin Simulator. This was the first ever simulation of a space flight. It tested life support systems, but also the mind of the person playing the role of astronaut under conditions of extreme isolation and confinement. This was one of the first tools Strughold wanted for his new Department of Space Medicine. It was basically a ground-based model of what they thought future spacecraft would be like. The basic plan was to seal a human inside there for a week and monitor them from the outside to see if they could survive, both physically and mentally. Strughold argued that if humans and machines were expected to perform together in space, they first needed to be tested together on the ground. Not only does Strughold's Space Cabin Simulator tell us about early spacecraft systems, the kind of person they chose to seal inside also tells us about the early astronaut. So Strughold began lobbying the Air Force in 1950 to build him one of these devices that he had thought up with his team. But the start of the Korean War meant that this forward-thinking space medicine stuff was sort of a low priority. So to convince the brass that this expensive new tool was absolutely necessary, Strughold constructed a wooden model of it in the department. And he also popularized it through illustrations like this one that appeared in Collier's magazine. In 1954, Strughold got his wish, and the first space cabin simulator arrived at the base. Because space medicine then was obscure, even at the School of Aviation Medicine, and the device so unwieldy, it was installed rather ironically downstairs in the basement. And here it is installed. So the space cabin simulator was incredibly cramped and confining. You can see a cutaway of it there. There were no windows, and by design, no way for the subject to communicate with the outside world. They would be totally isolated. The subject sat in a seat that folded out into a cot, but there was not enough room to stand up or even move around. The cabin was totally sealed environmentally. There was a thin artificial atmosphere equivalent to about 18,000 feet in altitude, and it was comprised of 40% oxygen instead of the usual 21%. An air conditioning system kept down the temperature and humidity, and carbon dioxide was removed through a non-renewable chemical process involving beryllium. The subject was supplied with tins of food and water. The kind of astronaut envisioned by this simulator was explicitly not a pilot. Strughold and his lead psychologist, Siegfried Garathewal, another German who came over in Operation Paperclip, viewed the astronaut as a passive systems monitor, more similar to a radar watcher. This idea of a passive, lower-skilled astronaut was reflected in the simulated work that they devised to keep the subject busy inside the simulator. Lights on this command panel, which we can see here at the left, would light up and basically tell the subject what task they had to complete next. The screen in the middle was where they conducted their simulated work, which was very similar to watching a radar. Basically, they were responding to lights, pushing buttons at the right moment, and that sort of thing. Because there was no day-night variation inside the simulator, or in space really, they decided to create a new work-rest cycle for the subject, and that was comprised basically of 4 hours of work, followed by 4 hours of rest, repeated over and over and over and over. Garathawal was an expert in the effects of monotony, isolation, and confinement, and wanted to see how the subject's performance at these tasks degraded over time, and whether they could be counted on to remain vigilant, one of the key virtues of the new Cold War, vigilance, and be counted on to act reliably on a moment's notice after spending days or even weeks inside one of these things. The subject could not see out of the simulator, but doctors and psychologists had many, many ways to see inside. You can see right next to the screen 2 closed-circuit cameras that provided a live video feed to the doctors on the outside. A still camera captured photographs. A concealed microphone recorded every word the subject uttered. The subject was also covered with biometric sensors that transmitted data to the doctors on the outside. The shell of the simulator was covered with peephole-like portholes that provided a one-way look in to the simulator. Additionally, the subject was given a logbook and encouraged to record their feelings during the simulated mission. The design of the simulator shows just how little autonomy and skill the early astronaut was assumed to have, and how ground controllers held all the power. While preparations for the first week-long test were being made, something momentous happened. The Soviet Union launched Sputnik, which suddenly put the spotlight on military space science to prove that America was ready. Sensing intense interest, Strughold billed the test as a week-long flight to the moon. The subject that Strughold selected to play the role of astronaut in the first space simulation wasn't a seasoned test pilot. It was a 23-year-old accounting clerk from the base's controller's office named Donald G. Farrell. After only 2 weeks of training, he was sealed inside the simulator with a mob of reporters watching. For the first few days, things went all right. Farrell attended to the simulated work, pushing buttons when indicated by the screen, and sometimes completing an hour-long math test. Sounds like fun. Problems began to crop up on the 3rd day when doctors signaled to Farrell that he needed to change the biometric sensors which were attached to his back. You can see them applying them there to him before he went into the simulator, but once he was inside, he had to reapply them himself, which was a painful and arduous process. So in his log, he wrote, quote, "Signaled back that I would accomplish the same after I finished what I was presently doing. Such inconsiderate people." On the 5th day, right when the make-believe spaceship would have been rounding the moon and heading back towards the Earth, Farrell's simulated work on the command panel tanked. And he wasn't sleeping well. He seemed restless and aimless. He had space cabin fever, basically. The feeling of constant surveillance was getting to him. After one incident, he wrote, "Ha, just caught someone peeping through the porthole covering at me. What a ridiculous situation, people sneaking around and peeping through tiny holes at me, getting a little anxious to get the hell out of this box." On the 7th day, hours before completing the mission, the doctors signaled to Farrell to change his biometric sensors yet again, and he lost it. In his logbook, he wrote, "Ha, I knew it. Got the change electrode signal. It never fails. 17 hours left in this blank blank, and now they want me to change electrodes? Got a good mind to tell them blank blank blank. Blank won't even give me hazardous pay duty for this ride, chintzy slobs." So when Farrell finally did get out of the simulator, one of the first people to rise and offer a hearty handshake was Lyndon Johnson, then the powerful Senate Majority Leader from Texas. Johnson had been a big supporter of Strughold's forward-thinking work since the early 1950s, and perfectly positioned for the cameras, he grinned and grabbed Farrell's hand, with Strughold there in the center looking on. Johnson considered this test a great success and took Strughold and Farrell on a whirlwind media tour to tout the nation's capabilities in space medicine. But back at SAM, the psychologists leafed through Farrell's expletive-laden diary and deemed the test a failure of the human component. Farrell was never let back in the simulator ever again. So this story of the very first spaceflight simulation shows an early version of a lower-skilled, non-pilot astronaut, one more akin to other push-button soldiers of the early Cold War. It also shows how tension between astronauts and ground crew started right at the very beginning in these simulations. And these continue today, and you can find evidence of these in the Apollo program, International Space Station. Happens all the time. So Strughold's space cabin simulator concept was quickly scaled up, and they built 2-person, 3-person simulators, and they got transferred all over the place to private aerospace companies, to NASA, and they became very common research tools, both in space medicine and in astronaut training at NASA. And simulation is now a major, major part of astronaut life. So it's important to understand how this all got started as a military science. The second case we're going to look at is called the Mount Evans acclimatization experiment. In July 1958, Bruno Balke, a German physiologist at the School of Aviation Medicine who also came over in Operation Paperclip, led a team of 6 young airmen on a 5-week-long trip to live and train at high altitude near the summit of Mount Evans in the Colorado Rockies. There we can see Bruno Balke. The goal was to see if acclimatization to low pressure would make future astronauts more oxygen efficient in spacecraft environments. Once they were on Mount Evans, Balke led the recruits in a rigorous physical training program, including jogging, climbing, and other calisthenic exercises. Then Balke and the airmen climbed inside this mobile pressure chamber that they had towed all the way up to the summit of the mountain, and got inside to see if they could remain conscious at even higher simulated altitudes. Now, Balke's background wasn't in aviation medicine or in flying. He was a mountaineer, and he had developed this experiment in a very different context. Back in Germany, in 1938, Balke had been part of a Nazi-funded mountaineering expedition to attempt to summit Nanga Parbat, one of the tallest mountains in the Himalayas. While most of the team were concerned with securing glory for the Third Reich, Balke's role was to study acclimatization for the Luftwaffe, the German Air Force. During World War II, Balke developed an acclimatization program for Luftwaffe fighter pilots at a high-altitude station in the Tyrolean Alps. About this experience, he wrote, quote, "Fighter pilots were trained under my guidance at the high-altitude station. Upon returning to their bases, they were able to exceed the altitude tolerance of non-acclimatized pilots by about 3,000 feet, a great advantage in air battle." So this was the model for his astronaut experiment on Mount Evans in 1958. Now, given his work for the Third Reich, it should come as no surprise that Balke's interest in acclimatization also included a long-running fascination with race. Many of Balke's studies took the form of comparisons between indigenous people adapted to high altitudes and white male soldiers. Balke believed that the bodies of high-altitude indigenous people held clues for turning white male soldiers into what he called a Superman for space. Now, once Balke had been hired by Strughold at SAM in Texas, he made the first of 3 trips to Morococha, Peru in 1953. This was an isolated mining town in the Peruvian Andes at about 14,000 feet. Here, miners endured many hardships extracting silver and copper for the Cerro de Pasco Mining Corporation. Medical facilities constructed to care for the miners also doubled as experimental laboratories. And in exchange for funding and equipment, the local authorities granted Balke and the US Air Force access to the miners as a population that they could experiment on. So Balke took these indigenous miners and put them in pressure chambers and timed how long they could remain conscious at increasing altitudes. Balke then attempted to train himself to surpass these benchmarks. What the indigenous Peruvians had acquired through centuries of long-term adaptation to low pressure, Balke sought to replicate through short-term acclimatization, accelerated by intense physical training at altitude. So this was the data that became the goal for his team of white male military model astronauts on Mount Evans. In his reports, Balke described indigenous Peruvians as well-suited for space, but he never considered them as potential astronauts. In a 1958 Air Force report, Balke wrote, quote, "Most of the prerequisites for astronauts are met by high-altitude natives. Therefore, it would seem feasible to attempt to train prospective crewmen as closely as possible to the physical standards of those natives. Life magazine summed it up simply as copying high-altitude Indians. So when space historians talk about race and astronauts, it's usually in the context of the civil rights movement in America in the 1960s and the slow integration of African Americans into NASA's astronaut corps. But this earlier episode from American military space medicine offers a new way to think about race and space. Older colonial ideas about race structured standards for the ideal astronaut body. The story of Belkey and the Peruvian miners adds the figure of the nationalistic mountaineer and the high-altitude indigenous person to the story of the early American astronaut. And this expedition to Mount Evans is also significant for being the very first Earth analog experiment in space medicine. Earth analogs are places on Earth seen as analogous in certain ways to environments in space. Today, expeditions to Earth analogs like deserts, the Arctic, deep caves, underwater habitats, and impact craters are common in space medicine and astronaut training. The third case we're going to look at is called the Lovelace Woman in Space Program. And this is the best known episode of the four I'll discuss today. It's the topic of a fantastic book by Margaret Whitekamp, a historian at the National Air and Space Museum, called Right Stuff, Wrong Sex. And last year it was also the subject of a Netflix documentary called Mercury 13. The basic story is that in 1959, space medicine expert Randolph Lovelace, that we can see there, initiated a privately funded study of women pilots for space fitness. Earlier that year, Lovelace, who was also head of NASA's Life Sciences Committee, was contracted to conduct the medical screening for NASA's all-male Project Mercury astronauts. Lovelace then wanted women to take the same tests to see if any would qualify to his standards. Lovelace reasoned that since women were on average smaller and lighter and consumed less food, water, and oxygen, that they might make more efficient astronauts than their male counterparts. Lovelace's first woman test subject was an accomplished pilot and aviation business executive named Geraldine Cobb, or Jerry Cobb for short. In August 1960, Lovelace announced his preliminary findings. Jerry Cobb had passed the tests and was fit for spaceflight. He then scaled up the program, recruiting 20 or so other women pilots. But media attention, like this article focused on Cobb, made NASA and the White House anxious, and support for Lovelace's continued testing of the women subjects quickly evaporated. He quietly canceled the program incompleted, and no American women flew in space until 1983, when Dr. Sally Ride was selected for the 7th Space Shuttle mission. One detail, though, that doesn't get a lot of attention in the story of the Lovelace Woman in Space program is Lovelace's military connections. The focus is often on how his clinic was technically a private foundation and separate from NASA, which was a civilian agency. But in many ways, the Lovelace Clinic was an extension of military space medicine. First off, Lovelace himself was an ex-Air Force flight surgeon who in World War II had developed oxygen equipment and high-altitude bailout techniques. In 1939, Lovelace actually traveled to Germany, to Berlin, and visited Strughold in his laboratory there in Berlin. And during the Lovelace Woman in Space program, the head of Lovelace's Department of Physiology was a doctor named Ulrich Luft, who had been Strughold's deputy in Berlin and was participating in Operation Paperclip. And coincidentally, Luft was also part of that expedition that Bruno Belkey was on to Nanga Parbat in 1938. The Lovelace Clinic also regularly partnered with the Air Force to screen pilots for covert high-altitude reconnaissance programs, including the CIA's U-2 spy plane and later the SR-71. In fact, the idea to study women pilots in the first place came from an Air Force officer, Lovelace's frequent and longtime collaborator on these projects, a brigadier general named Donald Flickinger, who Lovelace had met when they both trained together at the School of Aviation Medicine. So the only scientific publication to come out of the Lovelace Woman in Space program is this short article authored in 1964 by two of Lovelace's doctors, and it appeared in the Journal of Obstetrics and Gynecology. In this short article, the doctors focus on women's menstrual cycles and claim that they make them less reliable than men. and that their continued exclusion from spaceflight was medically justified based on this. Space medicine's strong conservative male bias began in the military, where well-studied male bodies were considered standard and normal components, and unfamiliar female bodies were mistrusted as complicated variants. So rather than see Lovelace's Woman in Space program as a moment where science said yes and society said no, I see it as a moment where stereotypes already present in space medicine were sort of imbued with this sense of scientific and medical validity. Now, the final case that we'll look at in this section on astronauts takes a detour from human to animal astronauts, and it's the case of two monkeys named Abel and Baker. In May 1959, the Army and the Navy collaborated on the test launch of a new type of nuclear missile called the Jupiter. It was launched from Cape Canaveral, Florida, but instead of containing a dummy warhead, as many of these tests did, the nose cone of this missile contained two live monkeys, a rhesus monkey named Abel and a smaller squirrel monkey named Baker. Military space medicine experts included monkeys because they considered them close physiological analogs to humans, and they wanted to understand the effects of rapid acceleration and weightlessness in rocket flight. Abel and Baker were not the first animals in space. America had actually been launching monkeys to space altitudes since 1949, and the Soviet Union had already orbited a dog named Laika 6 months previously. Abel and Baker are significant, though, because they're the first American animals to be recovered alive from a space flight. And because of this, they were able to go on to become America's first celebrity space animals. So after their successful recovery at sea in the Atlantic Ocean, Abel and Baker were flown directly to Washington, D.C. and presented to the public at this press conference held at NASA headquarters. NASA at that point was really just getting started, so they were hoping to kind of clamor on to this successful test by the Army and the Navy. So during the experiment, Abel and Baker served as scientific models for the human body. But after the experiment, they were converted into cultural models for future astronauts. Even though both Abel and Baker were female monkeys, Abel was popularized as a masculine and male astronaut, while Baker was fitted into the image of the suburban housewife. Confusion over Abel's sex and gender began right away at the post-flight press conference, where an Army general repeatedly referred to her as he. The assumption that Abel was a male monkey continued in the press, and you can see that here in this cartoon published only one day after the flight. Abel here is cast in the role of absentee husband, returning home late from work. Appearing guilty, Abel is being chastised by another monkey clutching a baby, clearly in the role of housewife. It's tough to see the caption there, but it reads, "Where the hell have you been?" After the NASA press conference, Abel underwent a surgical procedure at Fort Knox to remove an electrode that had been inserted inside her skin. But when the Army handlers anesthetized her, she stopped breathing, and Life magazine photographer captured these futile attempts to save her life. Abel died 3 days after the flight. News accounts of her death continued the confusion over her sex. The Chicago Tribune wrote, "A male monkey survived the flight, but he died on the operating table when an electrode was being removed." Another wrote, "Abel was dead, but he was not forgotten. He had been given full credit for the information his flight afforded." Following the autopsy, Abel was stuffed and remains on display to this day as a taxidermy exhibit at the Smithsonian National Air and Space Museum in Washington, D.C. This misgendering of Abel and the trope of the masculine American astronaut continues today. As recently as 2009, Abel was depicted in the 20th Century Fox family comedy Night at the Museum 2, Battle of the Smithsonian, where a magical artifact brings the Smithsonian's exhibits to life. In this movie, Abel is again hailed and referenced as a male character. In stark contrast, Baker, the smaller squirrel monkey supplied by the Navy, was without exception always accurately described as female and portrayed as feminine. The Navy scientist who selected Baker to make the flight was a physiologist named Dietrich Eberhard Bischer. He was one of the German scientists participating in Operation Paperclip. Following Baker's flight, Bischer immediately began to describe her in the way of a 1950s suburban housewife. saying, quote, "When she is about a year older, we hope she raises a family." Baker's cage was made into a domestic-themed public attraction called Baker's Bungalow. And soon everyone was calling her Miss Baker, the first lady of space. The school paired her with a male squirrel monkey named Big George that they called her husband, and even held a mock wedding ceremony for them that they publicized. Beecher wanted Baker to reproduce so that he could study her offspring for any abnormalities caused by radiation or magnetic fields in space. When Baker died in 1984, she was buried beneath this giant human-style gleaming marble headstone at the US Space and Rocket Center in Huntsville, Alabama. So even though no humans had flown in space at this point, gendered stereotypes of male and female astronauts were already on display in military space medicine's animal flights. So these 4 cases show that common features of astronaut selection and training, including simulations, Earth analog expeditions, medical screenings, animal tests, and studies structured around the categories of race and sex, have their origin in military space medicine. They also show a surprising array of test subjects modeling different aspects of the astronaut, ones that differ from the familiar white male military test pilot that NASA made famous during the space race. They help us to see that work on astronauts began as military projects well before NASA in the immediate aftermath of World War II and developed in concert with the early Cold War. They also show that the kind of person that space medicine experts came to consider right for space was not solely determined by technical requirements, but also by cultural ideas about bodies, minds, extreme environments, and technology. So now I'm going to switch gears and tell you about my next project, the one I'm working on here at the Linda Hall Library. It's about astrobiology, the study of potential extraterrestrial life, and how this field also began as a military space science. The main figure in this story is one we are already familiar with, Hubertus Strughold, the head of the Air Force's Department of Space Medicine. It turns out the whole time that he was working on astronauts, he was also thinking about where they might go, specifically the planet Mars. If Air Force astronauts made it to Mars, he wondered, what life might they encounter there? So here's our view of Mars today, supplied by NASA's Mars Reconnaissance Orbiter. But in the 1950s, when Strughold got started on this work, this was the best image of Mars. This is the best image of Mars that astronomers could produce through the most powerful telescope during the best time of seeing the red planet. This photo shows how much they had to learn about the planet, but at that time, astronomers already knew that Mars was very cold, very dry, and had a very thin atmosphere containing little to no oxygen. Despite these drawbacks, astronomers considered Mars the most hospitable place in the solar system other than Earth. In 1950, Strughold published his first paper about life on Mars, an internal Air Force report called Life on Mars in View of Physiological Principles. In 1952, his German countryman, Wernher von Braun, America's de facto space visionary at that point, published Das Mars Project, translated into English as The Mars Project, a detailed plan advocating for a large expedition there. With help from vivid artwork like this from Chesley Bonestell, he popularized the idea that missions to Mars could really happen. 1 year later, in 1953, Strughold published a book about life on Mars called The Green and Red Planet, a physiological study of the possibility of life on Mars. In it, he describes an experiment that he wants to conduct. Quote, "It would take only minor modifications and adjustments to a low-pressure chamber to construct a Mars chamber, capable of reproducing very nearly the exact environmental conditions, insofar as we know them, on that planet." Later that year, he conducted this experiment, but instead of using a large chamber, he simulated the Mars environment inside a jar. First, he called the device a Marsarium, after terrariums, but the name that caught hold around the base and stuck was Mars Jar. But simulating the cold and dry, rarefied conditions was only half the idea. Next, he sealed different kinds of microbes, bacteria, and vegetation inside that to see if any could survive, to see if life on other worlds was possible. Now, this was a really important moment in the history of space science. Before this, for centuries, the debate about life on other worlds, and on Mars in particular, had been the territory of philosophers, theologians, and most recently, astronomers. Before Strughold, the most advanced studies of Mars used a telescope, a spectrograph, and a thermocule, tools from astronomy, chemistry, and physics. Strughold was the very first biologist to study Mars, and the first to develop a biology-based experiment, a simulated environment, aimed at understanding extraterrestrial life. In his 1953 book, The Green and Red Planet, Strughold called his biological approach to life beyond the Earth astrobiology. In addition to naming the field and inventing its first tool, the Mars jar, he also organized the first astrobiology conference in early 1957 called Problems Common to Astronomy and Biology. By the time Strughold retired from the Air Force in 1968, he had amassed 25 publications just on the topic of life on Mars. Today, Strughold's invention, the Mars jar, remains a key tool for astrobiologists. They actually still call them Mars jars, although sometimes they call them by a more technical sounding name, Mars Environmental Simulators. What got my attention as a historian was that if you ask an astrobiologist today about the origin of their field or who invented the Mars jar, they tell you a totally different story. One that doesn't include Strughold at all, and one that takes place after his work in the 1950s, starting in the 1960s. Their standard origin story for their field is that following the launch of Sputnik in October 1957, Nobel Prize-winning molecular biologist Joshua Lederberg organized the field with funding from NASA. He recruited a young graduate student named Carl Sagan into the fold, and things really got going around 1960. This makes astrobiology seem like a product of the space race, emerging from within the peaceful civilian circuits of academic molecular biology and NASA, and leaves out Strughold and his decade of military work for the Air Force. To further distance their academic work from NASA, to further distance their academic work for NASA from Strughold's military work, Lederberg renamed the field. What Strughold had called astrobiology, Lederberg relabeled exobiology, short for extraterrestrial biology, at NASA. Exobiology remained the name of the field from 1960 until 1996, when NASA decided to rename it astrobiology again. I decided to recover this missing military origin of astrobiology by focusing on Strughold's Mars jar experiment. When I arrived at the Linda Hall Library for my fellowship, I wanted to understand this vision of Mars that Strughold was simulating inside the Mars jar. We all know Mars as the red planet, but Strughold's book is called The Green and Red Planet. What's that about? Where did green Mars come from? I had a general idea, a general understanding, that ideas about life on Mars had declined over the course of the 20th century. In 1894, American astronomer Percival Lowell believed he could see a network of canals on the surface of Mars, and he reasoned these must be evidence of an older, ancient, intelligent civilization. Today, astrobiologists hold out hope that they might discover microscopic microbial life or fossil evidence that it one time lived on Mars in the ancient past. Strughold's green Mars is a forgotten intermediary step in this scaling back of hopes for life on Mars. Strughold believed there was life on Mars, but that the harsh environment limited it to simple vegetation, like mosses, and especially lichens, the kinds of things you find growing high in the mountains. I wanted to know more about where Strughold got this idea from, and how controversial it was when he decided to bring biology to bear on the question of extraterrestrial life. For thousands of years, humans have recognized Mars in the night sky for its red appearance and associated it with fire, blood, death, and warfare. Likewise, the possibility of life elsewhere in the cosmos has an equally long intellectual history, going back at least to ancient Greece, and it was known as the plurality of worlds debate. Those speculations were mostly philosophical and theological in nature, having to do with big questions about the nature of the universe, the veracity of the Bible, the power and wisdom of the Creator. Believers in a plurality of worlds imagined other beings living on any number of celestial objects, and they did not single out Mars in particular. In the 1600s, people turned telescopes towards Mars for the first time, and it became more than just a red point of light in the sky. Between 1659 and 1683, the Dutch astronomer Christian Huygens viewed Mars through an early telescope and made these sketches, the first to show reliable surface features. We can see that Huygens differentiated between lighter areas and darker areas. And in the middle sketch, we can see that he also glimpsed a polar ice cap. Now, right from the start, Huygens assumed that these dark patches were oceans, bodies of water, and that the lighter areas were continents of land. Huygens also noted, after watching these for long periods of time, that the dark areas seemed to grow and shrink gradually over time, a phenomenon that later became known as seasonal changes on Mars. And we can see some 20th century photographs here. The left column is taken in spring, and the right column is taken in summer. And we can see that there's differences in the darker areas, darker shadings. So this was a mystery. They didn't know what caused this, and they had all these different theories. In the early 19th century, a British astronomer, John Herschel, noted that sometimes the dark areas on Mars appeared bluish-green. In 1832, German astronomers Wilhelm Beer and Johann Madler made the first attempt at mapping Mars, and we can see they used a greenish tint for the darker regions of Mars, which they also thought were oceans. An important moment for my story happens in 1860, when a nearly forgotten French astronomer working in Brazil named Emmanuel Liais hypothesized that the dark features on Mars were not oceans, but in fact vast tracts of vegetation. Liais noticed that these mysterious seasonal changes to the dark areas corresponded with the melting of the ice caps on the poles, and concluded that what he was seeing was the regular growth cycle of vegetation, regulated by the arrival and departure of liquid water from the poles. Liais's vegetation hypothesis is where the green in Strughold's green and red planet comes from. And we can see from around the same time that Liais had his vegetation hypothesis, this illustration from the French astronomer and popularizer Camille Flammarion, which imagined very tall cactuses on Mars and some intelligent inhabitants as well. But to me, the whole scene just seems like the American West. 1877 was a landmark year for human interest in Mars. The Italian astronomer Giovanni Schiaparelli published the sensational claim that he could see a complex network of straight lines on the surface of Mars. He produced this detailed map, but stopped short of saying anything about their origin. His claims ignited a Victorian-era sensation regarding life on Mars. After 1877, astronomers started to specialize in Mars, and Mars attained its special place in Western culture. Caught up in all this buzz about lines on Mars was the wealthy American aristocrat Percival Lowell, who constructed an observatory in Flagstaff, Arizona in 1894, specifically to study Schiaparelli's network of channels. Soon after, Lowell reported seeing even more channels than Schiaparelli and took the extra step of claiming that they were artificial constructions of an advanced civilization. This was a view that he popularized in a series of books, which are in the rare book collection here at the Linda Hall Library. When his collaborator, William Pickering, detected the absence of liquid water in Mars' spectra, Lowell incorporated this into his grand narrative. The civilization on Mars, he reasoned, must have built the canals to channel scarce water from the melting ice caps towards the equator in a desperate attempt to stave off drought. Liais's vegetation hypothesis factored into Lowell's theory as well. The darker regions were oases, and vegetation lined the canals as well. And here we can see a sketch from Percival Lowell, and we can see that he has included the darker areas in a greenish tint as well. So Lowell's popular book convinced many Americans that there really was an intelligent civilization on Mars, but he had his critics too. One of the most notable was Alfred Russel Wallace, the British naturalist famous for his co-discovery of natural selection, the one that pushed Darwin to publish Origin of Species in 1859. In 1903, at the age of 81, Wallace wrote a book called Man's Place in the Universe, which included a chapter pointedly aimed at Lowell, titled not so subtly, Earth is the only inhabitable planet in the solar system. Wallace argued that Mars was too cold, too arid, and too rarefied for creatures to exist. Wallace returned in 1907 with another salvo against Lowell, a book titled Is Mars Habitable? Spoiler, he says it's not. He wrote, for his conclusion, Mars, therefore, is not only uninhabited by intelligent beings, as Mr. Lowell postulates, but is absolutely uninhabitable. And he wrote uninhabitable in all caps. However, if you read Wallace's books, and we have them here in the collection at the Linda Hall Library, he leaves the door open a crack for Liese's vegetation hypothesis, conceding that despite the extreme conditions, quote, Mars may produce vegetable life of some low kinds. For most astronomers, Lowell's Martians were defeated, but the idea that vegetation caused the seasonal changes to the dark areas lived on. When new spectral data turned up bad news for plants, a lack of chlorophyll, and a lack of oxygen that plants produce in abundance on Earth, the vegetation hypothesis adapted. Russian astronomer Gavril Tikhov argued that simple hardy vegetation like lichens that grow in the cold, thin, dry mountain environment still fit the bill and were likely similar to what was growing all over Mars. This was the state of thinking about life on Mars when Strughold arrived in Texas after World War II. European and American astronomers, straining to see through increasingly large telescopes and studying spectral data, seemed to favor Liese's vegetation hypothesis. A survey of books about Mars written between 1940 and 1950 reveals that virtually all astronomers believed there was life on Mars, and that this life was almost certainly vegetation similar to lichens. Strughold recalled making his first Mars jar in 1953. Quote, I feared it would sound a little far-fetched, even to the open-minded men with whom I was working, to say, I wanted to simulate the Martian conditions. So instead of doing this at the Air Force laboratory, I bought a jar and a thermometer and started the experiment at home. I collected lava material with some moss lichens on it from Grant, Arizona. I put the jars in the ice box at night and in my kitchen by day. After 14 days, the lichens were still alive, but the experiment was incomplete because I had only studied the temperature ranges on Mars. Finally, I discussed this with Colonel Henry M. Sweeney, who was the director of research at the School of Aviation Medicine, and he immediately invited me to bring the experiment into the laboratory where we could simulate all other factors. In 1956, Strughold conducted the first Mars jar experiment at the School of Aviation Medicine's microbiology laboratory. Airtight jars were filled with an all-nitrogen, low-pressure atmosphere that on Earth was equivalent to about 78,000 feet in altitude. Martian soil was simulated using red sandstone mixed with lava collected from Arizona's Painted Desert, which was sterilized and desiccated. To these conditions were added different microorganisms, including lichens, bacteria, yeast, and fungi. To simulate the Mars day-night cycle, which is very close to Earth's, the team moved the jar system from room temperature to freezers set to minus 25 degrees centigrade at night. After 10 months, they cracked open the Mars jars and went searching for signs of life. What they found was that some microbes had managed to survive. But as you might have already guessed, the United States Air Force wasn't interested in potential life on Mars for the thrill of discovery or to settle some long-standing philosophical questions about the plurality of worlds. In case it wasn't obvious to his fellow military readers, Strughold stressed that knowledge gleaned from Mars jars had military applications. They would aid in man's survival on extraterrestrial bases, and that, quote, the ultimate goal is to determine if simple forms of life can not only survive and multiply, but contribute some product or perform some function required to support man in extraterrestrial situations, specifically the long-term operations of an extraterrestrial exploratory base. So, built into the Mars jar is the idea that Mars might become a strategic place for Cold War operations requiring an American military presence, and that any life discovered there should be used as a foothold. Now, when Joshua Lederberg rebooted the field at NASA as exobiology, His network of academic scientists adopted the Mars jar enthusiastically and even kept its catchy name. If you ask an astrobiologist today who invented the Mars jar, they will instantly tell you it was Carl Sagan. In his 1967 National Geographic article, Mars, A New World to Explore, Sagan wrote, quote, "In our laboratories, we have designed special chambers where we can simulate the Martian environment. They are, of course, called Mars jars." He also included them in his famous book and TV series Cosmos, leading them to become a common classroom teaching tool and a DIY space-themed activity kids could do at home. Mars jars are now associated with NASA and Carl Sagan, and not Strughold and the military in the 1950s. With Sagan as their new champion, Mars jars played an important role in the transition from green Mars to our current hopes for microbial life there. In 1965, NASA's Mariner 4 space probe sent back the first ever close-up photographs of the surface of Mars. Finally, centuries of debate about intelligent beings and canals and lichens could finally be settled. The result was a barren, crater-marked landscape that looked more like the moon than like the Earth. But Lederberg, Sagan, and the NASA exobiologists pointed to microbes living in their Mars jars as reasons to continue funding robotic missions to Mars to search for life anyway. These disappointing photos, they argued, didn't rule out the possibility of microbial life, which survived and even thrived inside their Mars jars. So why was Strughold written out of the origin story of astrobiology? It goes back to World War II. During the war, Strughold had been head of the German Luftwaffe's Institute for Aviation Medicine Research in Berlin. At the end of the war, reports emerged that researchers in aviation medicine had conducted lethal experiments on prisoners at Dachau concentration camp, killing roughly 700 people in low-pressure and freezing water experiments designed to aid Luftwaffe pilots. There is no evidence that Strughold was personally involved, but there is evidence that he knew what was going on. Although this evidence wasn't widely known until after Strughold's death in 1986, scientists like Lederberg and Sagan were certainly smart enough to know enough that they didn't want anything to do with this guy. So while Strughold is remembered as the father of space medicine, that created problems when these war crimes came to light. And buildings like this that had been named after him had to have his name chiseled off the side, and awards that were named in his honor had to be renamed something else. On the other hand, astrobiology did not have this problem because Strughold had been written out of the story right from the start anyway. But Strughold's invention, the Mars simulator, the Mars jar, continues to shape our understandings of Mars and human plans for that planet. Mars jars were invented to support one vision of Mars, the militarized green and red planet of the 1950s and the early Cold War. But in the 1960s, Mars jars were repurposed by Lederberg, Sagan, and academic exobiologists to craft our current idea of a microbial Mars. More than just tools, Mars jars work to organize, to popularize, and to naturalize a specific vision of a distant place, a Mars that is ours to colonize. Now, I hope you've enjoyed this survey of military space science before Apollo. Even though military space science before Apollo was obscure and not well funded, and not really a national priority like it was after Sputnik and at NASA, the influence of this early work reverberates through spaceflight and through space science today. And this last image demonstrates that. So Strughold never worked for NASA. He stayed in the Air Force right until his retirement in 1968. But this photograph shows him sitting in NASA Mission Control, chatting with Charles Berry, who was a flight surgeon for the Apollo program. This photograph was taken on July 20th, 1969, the day Neil Armstrong set foot on the moon. Thank you very much. I'd also like to thank the Linda Hall Library for hosting this talk, and extend a special thank you to Ben Gross, Eric Ward, Cindy Rogers, and John Rollins, who all helped with different aspects of this event. I also want to thank the rest of the wonderful staff here at the Linda Hall Library for their interest and support of my research over the past month. I arrived a fellow, and I hope I have left a friend.
Well, you have. We have time for a few questions. After the Q&A, and Marks, I'm going to have to step in front of you, excuse me. We have the camera with the live stream and video cameras right here. I wasn't in view over there, I guess. We have time for a few questions, and then afterwards, Jordan has a few books selected for display across the hall in History of Science, so you're welcome to join Dr. Bimm over there to look at the books and to talk with him. Just as a reminder, no food or drink in the History of Science reading room. So let's begin the Q&A with an online question. First of all, a comment. Ellie wrote, Jordan, you rock. So,
glad to know I still do.
Tony has a question. Do we know if the Russians had similar research going on at the same time? And I believe Tony typed this maybe during the first part of your talk about the humans in space and
space medicine, yeah, for sure. The expert in sort of the Russian space program, whose work I'll refer you to, is Asif Siddiqui. We do know that, in fact, they were working on similar things in aerospace medicine. One thing that differentiated the Russian work from the early American work, especially when space medicine transferred to NASA, was that the Russians spent a lot more time and put more emphasis on the psychological questions of outer space and psychological treatment of astronauts, whereas NASA, I think to their shame, just banished psychology and basically said they didn't want anything to do with those questions. They didn't want, a psychologist to embarrass an astronaut by disclosing some sort of mental problem, which was sort of stigmatized at that point, and unfortunately is still stigmatized today in space medicine and space operations. So the Russians actually were ahead of America in that respect, in actually taking the psychological problems of spaceflight very seriously and doing research into those as well.
So as you went through the archives, did you come across anything that made you say, huh, I did not know that?
You know what? So I conducted my research at a number of different archives. I went to the NASA archives in Washington, D.C. I went to the Air Force Historical Research Agency in Montgomery, Alabama at Maxwell Air Force Base. I went to the New Mexico Museum of Space History in Alamogordo, New Mexico. I went to the National Archives. I went to the Smithsonian. One of the things that really made me say, or ha, was after reading about a number of these experiments for years, I discovered film reel footage of them at the National Archives. And suddenly, these stories sprung to life in a way that I had never seen before. So I'd seen pictures of Farrell in the space cabin simulator, but now I was able to see him walking in, walking out. I had read about Bruno Balchi up on Mount Evans, and now I was able to see them running and jogging and hiking up there. And in fact, as part of my research, I actually visited the summit of Mount Evans to the exact spot where Bruno Balchi conducted that experiment, because I wanted to myself experience the effects of anoxia that they were there to study. So definitely the discovery of those film reels was a big aha moment. Thanks for that question.
As a physician, I've always been intrigued by a physician who is in aerospace medicine, who not only was the primary investigator, but was the primary subject. And this was a guy who was studying rapid acceleration and deceleration on rocket sleds.
STAP.
And I wonder if you have any comments of whether any of his work actually entered into the space program or not. It was largely, I think, designed for jet airplane flights and ejections, but certainly subjected himself to an enormous amount of damage.
So you're referencing a researcher named John Paul Stapp, who worked for the United States Air Force, and he worked out of Holloman Air Force Base in Alamogordo, New Mexico. And you're referencing a long rocket sled on a rail track. So what they did was they actually built a rail track, and they had a sled with a rocket on the back, and they would fire the rocket, and the sled would accelerate to tremendous speeds. And they would put animals on this, and then eventually they would put humans. And in the tradition of sort of this longer history of physiology and aviation medicine that space medicine comes out of, one facet of that is the self-experiment, is the idea that the researcher themselves was going to put their own body on the line and be the one to actually take it. So John Paul Stapp was that for these acceleration tests, and yes, it definitely was part of the space medicine story, and definitely was applied to accelerations that humans would experience during rocket flight. So not only were people being accelerated by tremendous speeds in rocket planes and jet-powered aircraft, rocket liftoffs created a similar acceleration on the body that could drain the blood and do lots of different things that are bad if you're trying to operate a craft. So John Paul Stapp and his Daisy Track, I think is what they called it, and Sonic Wind, I believe was the name of the sled. I was actually able to visit parts of the sledge at the New Mexico Museum of Space History, where they have them on display. I chose not to focus on Stapp and his experiments in my work because I was interested in looking at test subjects that sort of didn't fit the mold of the astronaut that we kind of already know about. And Stapp, as like, a white male military guy, was very much in the mold of the later astronauts, even though he wasn't an astronaut himself. So I felt like his story was already extremely well told and well known, and therefore I was very interested to learn about him. But I decided to direct my efforts elsewhere to stories that perhaps weren't so well known already.
We think of the space race as between Russia and the US, but from listening to your talk and the things that you said about Operation Paperclip, and I know that isn't it true too that the German scientists, some came to the US and others went to Russia? But if not for World War II, we would have more 3 countries like Germany, US, and Russia. And from everything you're sharing, it almost seems to me like Germany was the so advanced, how either Russia or the US would have come to where they did as quickly as they did without the German scientists. Is that anything that you reflect on, or is that, I hadn't thought about it till today.
Sure. Well, the migration, the immigration of German scientists to both America and the Soviet Union, more went to America than to the Soviet Union. Some actually went to the United Kingdom as well. Played a huge factor in the space race. And what's really interesting is that if you ever spend time in Germany, you can take a train 4 hours north of Berlin and visit Peenemünde, which is the rocket base on the Baltic coast, where I have spent some time. If you go there, it's basically deserted. And there's a huge museum there dedicated to the V2 rocket, which is what Wernher von Braun developed for the Nazi forces, one of their wonder weapons. And it was from Peenemünde in 1942 that the first human-made object actually went into outer space. It didn't go into orbit, but the nose cone of the rocket did reach what we consider space altitudes. So they refer to Peenemünde as the birthplace of spaceflight. So yeah, they definitely played a huge role. It's difficult, as a historian, I try and stay away from these counterfactual questions of, if the war didn't happen, what would Germany's space program, what would that have looked like? I think it's a very fantastic question in the real sense of the word fantasy, but I wouldn't want to weigh in on that, except to note that their influence in America was incredible. And oftentimes we get the rocket story with Wernher von Braun, and we understand the influence there. What's less well understood is the life sciences side, which is what I've tried to show. They were also heavily influential there as well. Thank you for the question.
Something that's kind of caught my eye over the years, looking at the early films and photographs of the primitive spacewalk, the Gemini and like that, looking at their spacesuits and comparing that with the current types of extravehicular suits that the astronauts wear. There's such a huge difference in material in those, and it makes you wonder, were those early suits very uncomfortable temperature-wise outside the vehicles? They're so thin compared with the more bulkier uniforms you see today.
Yes, the short answer is they're incredibly uncomfortable temperature-wise, and astronauts, struggled with those suits. There's a famous story about how Ed White, the first American to spacewalk, almost didn't make it back inside the capsule because of the way the suit changed in the vacuum environment of space. In terms of the material story, what's really interesting there is, the early spacesuits were sort of this sprayed-on silvery color that was meant to sort of disguise the fact that they were actually, basically copies of an earlier Navy suit, the Mark IV suit, and they were sort of sprayed with this aluminum exterior to give them a sort of a space-age kind of pizzazz. And that's actually a metaphor that I use in my story about the astronaut, which is that the astronaut was also, like the early spacesuit, was a military creation that sort of was given this sort of, space-age kind of veneer. And that if you go just below the surface, you get to this whole military story, not just about the spacesuit, but about the person inside the spacesuit as well. And it's interesting to note that after Project Gemini, the spacesuit became colored white, and the reason for that has an entirely different long history, which I've written about elsewhere in a chapter I co-authored with a colleague named Patrick Killian in Germany. And it goes back to tests about the atomic bomb and the reflecting properties of different materials, different colors. And it's a fascinating story. Our article is called "The Well-Tempered Astronaut," and the story about the color of the spacesuit and the different properties and everything there has a fascinating backstory as well, which I'll just tease here and let you find.
Right, Jordan, due to the time, let's do one more question. I believe your hand up here, and then we'll move across the hall to our History of Science reading room.
Excellent.
Jordan, I enjoyed your presentation. I had a question about one of the slides at the conclusion of your first presentation when you showed all four pictures. And on the lower left side with Jerry Bob, she's sitting in a dental chair with an Emerson basin and a hypodermic needle, and I was wondering what that was about.
Yes, so Jerry Cobb in that picture is actually having her muscles stimulated with an electrical current that is going into her arm, and that will make your arm basically go like this uncontrollably. It's incredibly uncomfortable. I've heard some, so Jerry Cobb, when she sort of started her campaign to get NASA to create this sort of, parallel women in space program, she called the organization of the different women test subjects the flats for the fellow lady astronaut trainees. And there's been a lot of pushback from certain people in the space history community who argue that's a misnomer because they didn't receive training, they were only test subjects. But I would argue that to go through a week of tests at the Lovelace Clinic and then go to the Wright Air Development Center at Wright-Patterson Air Force Base and go through all the psychomotor tests there, that effectively is a form of astronaut training as well, and that name actually does stand.
Right, Jordan, thank you for a wonderful talk.
Thank you very much.